People mix up voltage, power, and energy all the time. We throw these words around like they're interchangeable, but they are absolutely not. And getting them wrong isn't just some tiny mistake. No, seriously, here's the deal. Confusing them can literally destroy your circuit. So if you really want to understand how electricity actually works, from charging your phone to building your own electronics, you have to get this right. The best way to think about it is like they're three different players on the exact same team. They're all connected, they all work together in the same system, but each one has a very specific and very different job to do. So let's break down exactly what those jobs are. And look, this isn't just a mistake that beginners make. I hear professionals get sloppy with these terms, and that's when things can get risky. Let's look at some of the most common and, frankly, most dangerous assumptions people make. This is a classic one. You've probably heard it, right? Just crank up the voltage and boom, you've got more power. Well, not quite. It's a huge piece of the puzzle, for sure, but it is not the whole story. And we're about to see why just assuming that can get you into a whole lot of trouble. Okay, this one might just be the biggest offender of them all. People use power and energy as if they're synonyms. I mean, think about it. Your utility company bills you for the energy you use, not the power. There is an absolutely crucial difference, and understanding it is everything. And finally, we've got the big one, the fear factor. You see the signs everywhere, right? Danger, high voltage. And yeah, high voltage can be super dangerous. But think about this. A little static shock from a doorknob can be thousands of volts, and it just gives you a little zap. So what gives? It turns out voltage is only one part of what makes electricity dangerous. The real story is, as always, a little more interesting. So, how in the world do we untangle all this? Well, there's a really simple, really intuitive analogy that makes it all just click. Let's imagine electricity is just water flowing through a system of pipes and hoses. First up, we have voltage. So I want you to picture voltage as the water pressure inside a tank. It's the potential, the force that's just waiting to push that water out. More pressure means a stronger potential push. But notice, no water is actually flowing yet. It's just sitting there, ready to go. Voltage is simply the push. Okay, now let's open the valve. Power is the actual flow rate of the water shooting out of the hose. It's how much water is moving every single second. It's the rate at which work is being done right now. A gushing fire hose? That's high power. A slow drip from a leaky faucet? That's super low power. And all that leads us to energy. Energy is the total amount of water you've collected in a bucket. And it depends on two things, right? How fast the water was flowing, that's the power, and for how long you left the hose on, that's time. Okay, that water analogy is perfect for building your intuition. But now, let's get real and connect it to this simple math that actually governs all of this. This is where it all truly comes together. So remember how power was the flow rate? Well, that flow isn't just about the pressure or the voltage. It also depends on how wide the pipe is. And in electricity, we call the flow through that pipe current. So you need both the push, which is voltage, and the flow itself, current, to figure out your total power. And here it is, the big aha moment. Energy is simply power multiplied by time. This is it. This formula perfectly shows you why they are not the same thing. Power is what's happening in an instant, but energy is the total accumulation of that power over a duration. All right, let's make this super concrete with a perfect, real-world example that I guarantee you have at home. An electric kettle going head-to-head with a phone charger. Your electric kettle is a high-power beast. It's like that fire hose we talked about, using a massive flow of electricity to boil water in just a minute or two. Your phone charger, though, it's the total opposite. It's a slow drip, just sipping a tiny bit of electricity for hours and hours on end. So here's the key takeaway. Even though the kettle has way, way higher power, if you leave your phone plugged in all night, it might actually end up using a similar amount of total energy as boiling that one pot of water. High power does not automatically mean high energy. It always depends on time. Okay, we have covered a lot. The dangerous mix-ups, the water analogy, the formulas, the real-world example. So let's boil it all down to one simple three-part summary you can take with you. This is it, right here. Voltage is the potential. It's the push. Power is the rate of work getting done right now. It's the action. And energy is the total amount of work that's been done over a period of time. So remember, voltage pushes, power works and energy accumulates. So, now I want to hear from you. Before watching this, which one of these three, voltage, power, or energy, gave you the most trouble? Drop a comment and let me know. And hey, make sure you're ready for the next explainer because we are going to take everything we learned today and apply it to some real circuits. You are not going to want to miss it.